Hi, I'm Mark Barsamian. In this video, I'll be discussing content from section 4.2 of Susanna Epp's book, Discrete Mathematics. I see these notes have a typo. This should say section 4.2. The title for this section is Writing Advice. This section is basically a series of examples of types of proofs and discussion of kinds of things that can come up in writing proofs. So that's a very vague title, but it's actually sort of accurate. Now remember that in section 4.1 and in the video for section 4.1, we discussed proofs about only very basic concepts, even and odd numbers, and composite numbers and prime numbers. And the proof structures that we used in section 4.1 were very basic as well. So we had proofs involving proving true existential statements. Examples were used to prove those. And we had examples where we disproved false universal statements, and examples were used to prove those as well. Those were called counterexamples. And then we had some proofs that were proofs of universal statements, and they had to be proved by generalizing from the generic particular. And in a special case of that, universal statements that were universal conditional statements, when we applied that method of generalizing from the generic particular, the resulting structure is called the method of direct proof. So for reference, I've included the definitions of those things on the next 3 pages. So the definition of even and odd numbers was to say that n is even means that this existential statement is true. To say that n is odd means that this existential statement is true. To say that n is composite means that this existential statement is true. And to say that n is prime means that this and statement is true. And here's a reminder that to prove an existential statement, a statement that says there exists some x in the domain such that p of x, you have to produce an example of an x in the domain that makes the predicate true. And to disprove a universal statement of this form for all x in D, p of x, you have to produce an example that makes p of x false. Such an example is called the counterexample. And in the case where the domain is a finite set, a universal statement can be proven by confirming that every element of the domain makes p of x true. This method is called the method of exhaustion. But for proofs of universal statements that have domains that are infinite sets, we have to do general proofs. So generalizing from the generic particular. And if the universal statement is of a form that's a universal conditional statement, the generalizing from the generic particular becomes this what's called the method of direct proof. So no new math concepts are introduced in section 4.2. The author just makes recommendations for writing proofs. I'll do various examples as well. There is one new math concept that comes up in some of the exercises and that I will consider in an example in this video, and that's the idea of consecutive integers. So here's the definition. The words two consecutive integers mean two numbers of the form m plus 1, where m is an integer. And that idea generalizes. So for instance, 4 consecutive integers could be numbers of the form m plus 1, m plus 2, and m plus 3. So that's fairly straightforward. But this form can vary. So for instance, 2 consecutive integers could be of the form m minus 1 and m instead of m and m plus 1. And 4 consecutive integers could be of this form, m minus 2, m minus 1, m and m plus 1, where m is some integer. So as I said earlier, I'll just do a series of examples and discuss issues as they come up. So, example 1, prove the following statement. If m is any odd integer and n is any even integer, then m squared plus n squared is odd. So let's start by putting this in the form of a universal conditional statement. So there's our statement rewritten formally. Notice that it's a universal statement because it says for all m and n in the integers, and it's a universal conditional statement. So it has the form if A, then B. So remember the proof structure that we should use. We should use the structure that's called direct proof. To prove a statement of that form, we start by doing this stuff. We suppose X is a particular but arbitrarily chosen element of the domain for which the hypothesis is true. So that's the start. So that's the given stuff. That's why we say suppose. We don't prove that. That's what we're supposed to start with. So let's go back up and look at our proof structure again. That's what we did here. This is item 2 on the method of direct proof. Now, how does this proof end? Let's think about the frame. We show that the conclusion Q of X is true. Well, let's go down and look at this. So this is like our P, capital P, and this is like our Q. So that Q needs to appear as the very last statement of the proof. So that's the first thing to think about when you are building a proof. Look at the structure of the statement you're going to be proving and think about the frame of your proof. Now, I want to save this image as something that can be referred to later. So what I'm going to do is copy this whole proof structure and put it on the next page where we'll begin to fill it in. So I will not bother you with the tedious details of that. We'll scroll down and find it there waiting. So there I've put a copy of that proof structure. Now I've erased the word structure because we're actually going to start filling in this proof. So you can see that that's the frame of the proof. That's the direct proof frame that we know has to be the frame just because of the form of the statement that we're trying to prove. We're trying to prove a universal conditional statement. So the description of the domain and the hypothesis goes into step 1, and the conclusion shows up as the very last step of the whole proof. Now let's think about some other stuff that is inevitable. First of all, notice that step 1 includes this phrase, m is odd, and it also includes this phrase, n is even. So that's stuff that we know is true, but it's expressed in an abbreviated form using defined terms. So m is odd. That's just a 3-word sentence. So we have no choice what we have to do next. We have to use the definition of odd to write down what that really means. So that's going to go on step 2. So in step 2, we could say that we unpacked the definition of odd. Step 1, we have this very compact statement, m is odd. In statement 2, we have a much more wordy statement of what that really means. Step 3, we have no choice about as well. We have to unpack the definition of even. So there are 2 lines that we have no choice about. There's no mystery about that. Now let's look forward to the end of the proof. The end of the proof includes this phrase, m squared plus n squared is odd. Well, the only way that we can justify that is on the previous step we have to have proven the stuff that really means m squared plus n squared is odd. So in other words, the previous statement will have to be the following. So we see that the second to the last line is going to have to be this black statement, because that's what it really means to say that m squared plus n squared is odd. So the only way to get to the last statement of the proof, the blue statement, is to have it preceded by that other statement. And when we do finally get to the last statement of the proof, we know how it's going to be justified. The last statement of the proof, this blue statement, is going to be justified by the previous statement and the definition of odd. So in going from the second to the last statement to the last statement, we are packing up the definition of odd. We're taking all of this stuff, which is a very wordy sentence, and we're restating it in a more abbreviated, concise way using a defined term. So we have no choice about the green, red, and black statements, just as we have no choice about those blue statements that are the frame of the proof. Now you can see that the proof has a much smaller gap that is mysterious. This is the gap that we're dealing with having to fill in now. Well, I want to preserve this state of the proof as it is, so I'm going to copy all of this stuff, put it on the next page, and when I'm done, we'll scroll down and resume there. All right, so here is the state of the proof as we left it in the last page. So we have the blue outer frame, and then the green, red, and black statements that had to be there because we were using defined terms. So now our goal is to try to fill in the gap. So if you look forward to the end of the gap, you see that we have this equation that we want to be true. Now we don't have an integer h yet, but we do have m and n. We know something about them. M is this thing, and n is this thing. So we have the things that we need to build the left side of the equation that we need. So what we should do is just build that and see where it leads us. So statement 4, we're just going to build the left side of the equation that we need. One comment here before going on. Notice that on the previous page, I should have talked about this then, I used the definition of odd here. There exists an integer k such that m equals 2k plus 1. The next step, I used the definition of even, but I didn't use the letter k again. K has already been used up, so I had to come up with a different letter. So I introduced the letter j. And down at the very end, when I wanted to use the definition of odd again, I had to come up with another letter. So I came up with the letter h. So I didn't just keep using k. Go back and look at the definitions of even and odd. Even and odd both use the letter k in the definitions, but when you actually use these definitions in a proof, you can't always use the letter k. If k has already been used, you've got to use some other letter. All right, so we've built the left side of the equation that we need. We need to end with this equation, and the left side of that is that blue circled thing. So we started with that, and then we substituted in the things that we knew about m and n. Now let's keep going. Let's rewrite this right side. Now look, where we need to get to where the right side is this. So we want 2 times some integer plus 1. So let's rearrange the right side of our equation. Notice we have the plus 1 that we need. We want to have a plus 1 here, and we've got a plus 1. Now, the other thing that we want is we want to have 2 times something that's an integer called h. Well, look, that stuff that's circled green is going to have to play the role of the 2h. So let's make it really straightforward and factor out a factor of 2. Now we can see very clearly what we should do. We need to have an h there, a 2h, and so this is going to have to be our h. So we have no choice about what we need to do next. Statement 5 should be to introduce the letter h. So there's our h. Now we're actually ready to put numbers on these ending statements. This double asterisk statement, it's going to have to be statement 6. And the justification for statement 6 is by 4 and 5. And the very last statement of the proof is going to have to be statement number 7. And the justification for that statement is going to have to be by statement 6 and the definition of odd. So I'm going to leave this color coding here because it gives a little bit of an idea of when stuff happened. The blue frame happened first, and then the red, green, and black statements happened second, and then the blue core of the proof happened last. So chronologically, the proof was built very different from the way the proof step numbers would indicate. All right, that's the end of that example. Let's go on to the next example. Example 2 is to disprove the following statement. There exists an integer k greater than or equal to 4 such that 2k squared minus 5k plus 2 is prime. So we have to disprove this statement. So this is an existential statement. Remember, to prove existential statements, you just provide an example. But to disprove an existential statement, well, that's more complicated. Let's call this statement S. So let's write S formally. To write S formally, we need to have a symbol for the domain. So let's let the domain be denoted by the letter D, but let's write what D is. So with that symbol for the domain, it's fairly easy to write statement S. So there's the formal statement of S. Now we can build the negation of S. And remember how we make more sense of negated statements, negated quantified statements. We move the negation as far as we can to the right. So we move the negation past that first quantifier, and it will change that existential quantifier to a universal quantifier. So now the negation is parked in front of our predicate. Let's move it farther to the right by negating the predicate. All right, so there's our negation of statement S. Notice the negation of S is a universal statement. So statement S is an existential statement, but it's a false statement, and we're trying to disprove it. That means that we're trying to prove negation S. Negation S is a universal statement, and those have to be proven with general proofs. All right, so let's remember how we structure a general proof. We have to do this, generalizing from the generic particular. We have to show that every element of some set satisfies some property. We have to start by supposing is a particular but arbitrary element of that set, and then show that X satisfies that property. That's very vague. So let's look again at our structure. We're supposed to show that every K that's in D satisfies this property, has this property. So our proof structure is that we need to start the proof by saying, suppose we have one of these, and we need to end the proof by proving that it has that property. So let's write out the proof structure and then see if we can fill it in. So our proof has to begin with that. Suppose that K is an element of D, a generic particular element. Now, what we have to prove is that K has the property that's mentioned in the predicate. We have to show that K has this property. Well, so that circled statement needs to be the last statement of our proof. 2k squared minus 5k plus 2 is not prime. That has to be our last statement. Now, we don't know how we're going to get here, so we just have to say that there's going to be some justification. And that'll be the end of the proof. Okay, I want to save that proof structure, so I'm going to copy it and put it on the next page. So now we'll scroll down and find this proof structure copied, and we'll start to fill it in. So there's the proof structure that we just copied. Now, how on earth do we prove this? Well, we know that we want to have this statement proven, and that statement involves this quantity, 2k squared minus 5k plus 2. So let's just build that quantity and see where it leads us. So I'm going to clear out this middle part. Well, what do we do with this? Well, think about where we want to go. We want to show that that quantity is not prime. Prime has to do with whether you can factor things. So let's see if we can factor that expression. There's a factorization. When you multiply those terms out, let's check. So our check worked. Oh, so look, that expression there can be factored. Now, does that mean that that expression is not prime since it can be factored? Well, we have to be careful. Remember the definition of prime. A prime number is one such that the number is an integer, it's greater than 1, and it is not composite. So if any of those things fails, then our number cannot be prime. Well, let's see if we can prove that our number is composite. Let's go up here. The definition of composite numbers is that the number can be factored where both of the factors are greater than 1. Let's go back down and look at our factorization and see what we can say about the sizes of those factors. Well, we know something about k. We know that k is in the set capital D. So k is an integer and it's greater than or equal to 4. Now let's think about the factors that we have and how big they are. Let's call this left factor r. So since k is greater than or equal to 4, that tells us that r is greater than or equal to 7. And let's look at the other factor. Let's call that factor k minus 2. Let's call that s. How big is that? Well, again, k is greater than or equal to 4, so that means that s is greater than or equal to 2. So let's summarize what we've found so far. So we found a factorization for our quantity. It can be factored as r times s, where r is greater than or equal to 7, and s is greater than or equal to 2. Well, let's go back up and look again at our definitions. We have been able to factor our expression as r times s, where both of those numbers are greater than 1. So that tells us that our expression is composite. So we can follow up statement 3 by saying that our expression is composite by statement 3 and the definition of composite. Now, since that quantity is composite, we can say that it is not prime. Why? Well, let's go back up and look again at the definition of prime. For a number to be prime, it's got to satisfy all these things. In particular, the number has to not be composite. We just showed that our number is composite. Since our number is composite, that means it cannot be prime, and that's by definition of prime. So this last statement of the proof is statement 5, and the justification for statement 5 is by statement 4 and the definition of prime. That's the end of that example. Let's go on to the next. Prove or disprove. For all integers m and n, if n minus m is even, then n cubed minus m cubed, this is a typo, should say m cubed, is even. We're not told whether this is true or false. Well, shoot. So we're not sure if this is true or false. What can we do? Well, let's just experiment with some values of m and n. So my first pair that I'm trying is just m equals 1 and n equals 3. Then the difference is the number 2, which is even. Let's see what the difference of the cubes is. Well, the difference of their cubes is even as well. Let's try another one. Let's try maybe 1 and 5. Okay, well in this case, the difference of the numbers is even, and the difference of their cubes is even. Well, let's try something else. Maybe we'll try some even numbers. M equals 2, n equals 4. Well, dang, every time we come up with some m and n numbers that make this number even, it seems like that number is even as well. Well, shoot, that's frustrating, because if we had just found a single example where this number was even and this number was not even, that one example would be a counterexample that would prove our statement false. But the thing is, if our statement is true, then no number of examples is going to be sufficient to prove that it's true, because it's a universal statement. So let me say it again. Our statement seems to be true. Our statement is a universal statement, so we can't prove it by examples. We have to do a general proof. So let's think about the proof structure that we would need for a proof of this statement. So the statement that we're trying to prove is this statement S. So the proof structure would have to be that we would start with a generic element of the domain that has this property. Because we're using the method of generalizing from the generic particular element. This style of proof, actually it's this, applied to a conditional statement, we're going to use the method of direct proof. So we start by supposing that we have a particular element of the domain, a particular but arbitrarily chosen element for which the hypothesis is true. And then our proof is going to end by having shown that the conclusion is true. So I don't know how we're going to get here, but we're going to have to end by So that's our proof structure. That's our frame, the direct proof frame. We have no choice about that. In the first line of the proof, we have all of the green stuff, the description of the domain and the hypothesis. The very last statement of the proof we have no choice about. It's got to be whatever is in the conclusion. Now on the next page, I'll copy this frame down, and we'll fill in one more layer that we know that we have to have. So how can we begin to fill this in? Well, notice that we have a defined expression here. N minus m is even. We have no choice about what's going to have to happen on step 2. And notice at the end, we have a defined expression. n cubed minus m cubed is even. That means something. We have no choice about how this is going to end. Not only do we know that those statements have to be there, we know how they're going to be justified. Statement 2 is by the definition of even. Now, the red statement we don't know the justification for, but the final statement we know how it's going to have to be justified. So there's our proof structure filled in with a couple more inevitable steps. So this is the frame, the blue frame, and then the green and red statements that we have no choice about because we're using defined terms. There and there. Those defined terms have to be used in a proof in a certain way. Well, so I will copy this proof structure filled in a little bit like it is onto the next page, and we'll fill it in some more there. So there's the proof structure that we have so far. Now, how can we fill this in? Well, notice that the place we're trying to get to is this equation. The left side of that equation we can do something with. Let's start a statement 4 by just simply writing down the left side of that equation. There's a trick here. It's not really a trick. You all are probably a little bit rusty with factoring, but let's factor this. It turns out that n cubed minus m cubed always factors. Now, you might not remember that, so let's check and make sure that we believe this. Now, to check this, we have to multiply all these terms together. Notice that a bunch of terms cancel. This term cancels that term, and this term cancels that term, and I end up with n cubed minus m cubed. So it does work. Okay, now we have that factorization. Oh, but look, we know something about n minus m. We know that n minus m is 2k. We use the result of step 2. Looks like I've numbered my steps wrong. This should be step 3. Now look where we need to get. We need to get to this equation down here that says n cubed minus m cubed equals 2 times some number j. Well, look what we've got. We've got n cubed minus m cubed equals this thing. We are so close. All we need to do is let this stuff be j. So that'll be our step 4. Now, it's not just enough to let j be something, to make sure that we have the term that we need. We have to point out that it is an integer. So now we're ready to renumber this red statement. This red statement is actually statement 5. So what's the justification for it? The justification is by statement 4 and statement 3. And then we're ready to renumber the final blue statement. The final blue statement is going to be number 6, and it's going to be justified by the previous statement 5 and the definition of even. So there's our final proof. That's the end of that example. Let's go on to the next example. Example 4 is prove or disprove. For every integer m, if m is greater than 2, then m squared minus 4 is composite. Well, we're not told whether that's true or not, so let's just experiment. So we just need to try some values of m that are greater than 2 to see if we believe this statement is true or think that maybe it's false. Oh, geez, the very first number that we try, m equals 3, the first number that we can think of that's greater than 2, when I compute m squared minus 4, I get the number 5. That's prime. So our statement is false, and the proof that it's false is this counterexample. m equals 3 is a number that is greater than 2, an integer that is greater than 2, and such that 3 squared minus 4 is not composite. That stuff that I just spoke out loud is worth writing. You want to hit the reader over the head with this so it's so clear they understand why the statement is false. That should say 3. So the explanation is you present the counterexample and you hit the reader over the head with it. You make sure they understand why that's a counterexample. Okay, let's go on to the next example. Statement 5. Prove or disprove the following statement. The difference of the squares of any two consecutive integers is odd. Now, we would like to figure out how to structure a proof of this, so it would be nice to state this formally. So we want to use quantifiers, variables, domains. The question is, how many variables? What should they be called? You might think that we need 2 variables, like maybe m and n, because we have consecutive integers, so we're talking about 2 integers. But it turns out that we don't really need 2 variables, and the problem is a lot simpler if we don't use 2 variables. So before we write this symbolically, let's recall what we know about consecutive integers. We know from earlier in the video, the very beginning of the video, that consecutive integers can always be written in this form, m, m plus 1, for some m that's an integer. So for instance, the consecutive integers 66 and 67. Well, for that pair of integers, the value of m would be 66. For the numbers negative 54, negative 55, well, that's actually kind of written backwards. We should think of those as negative 55, comma, negative 54. For that pair of consecutive integers, the value of m would be negative 55. So if we want to describe a pair of consecutive integers, all we really need to do is give the first integer, the one that's on the left, and that really describes the pair. So a quantified restatement of our statement that we're trying to prove or disprove would look like this. That is a formal restatement of the statement that we're trying to prove. That's how the statement actually reads formally. For all m that are integers, this thing is odd. So you see that what we have here is the square of the integer m and then the square of the next integer, m plus 1. So this is the difference of the squares of 2 consecutive integers. So that expression is the difference of the squares of 2 consecutive integers. And the fact that m can be any integer, that takes care of all possible pairs of consecutive integers. Any pair of consecutive integers can be achieved by choosing the appropriate value of m. So doing this quantifier with a single variable takes care of all pairs of consecutive integers. So that's the formal statement that we need to prove. We see that it's a universal statement, and the predicate is this thing. So how can we prove or disprove that? Well, let's see if we think it's true. Let's choose some values for m. Well, it seems like the result is always odd, but let's try some negative numbers just for kicks. And let's try a pair where one of the numbers is 0. So it seems that this statement is true. So we need a general proof. So let's do that on the next page. So let's copy this statement onto the next page and prove it. So there's the statement that we're trying to prove. So our proof structure needs to be a generalization from a generic particular element. So how does that proof structure go? Well, remember that it starts by saying, suppose that you have some randomly chosen element of the domain. And the proof has to end by having this statement with some justification. And that'll be the end of the proof. All right, well, let's copy this frame onto the next page and see if we can fill it in. I'm going to copy it and have it ready so that when we scroll down, we'll find it. So there is our existing proof frame. Now, what do we know that we have to fill in? Well, look how this is going to end. M plus 1 squared minus m squared is odd. That's a defined term. We know that we have no choice. Before that last statement, we're going to have a previous statement that's what it really means to have an odd number. So we know that the previous statement, it's going to have to be this big statement, because that's what it means to say that that expression is odd. So we have no choice about that red statement having to be there. We don't know how we're going to justify that statement, but we do know how we're going to justify the last statement of the proof. So we can change this and now we know how the last statement is going to be justified. It's going to be justified by the second to last statement and the definition of odd. So that blue frame is inevitable. We have to have that frame to prove a universal statement. And furthermore, that red line and that justification has to be there because we have to deal with this defined term. Now let's see if we can fill in this proof. I'm going to put a copy of this on the next page, and when we scroll down, we'll find it. So there's that same structure filled in a little bit, copied, moved down here. Now see if we can fill this in. We want to get to this equation being true. So let's build the left side of this equation and just see where it leads us. Well, look at that. M plus 1 squared minus m squared equals this expression. And look, we wanted to say that m plus 1 squared minus m squared equals that expression, 2k plus 1. So all we need to do is introduce our k and point out that k is an integer. And now we're ready to renumber that red step. That red step is going to have to be statement 4, and that is going to have to be justified by statements 2 and 3. And our last statement of the proof is going to have to be numbered statement 5, and its justification is going to have to be by statement 4 and the definition of odd. So now you see that we've filled in the entire proof. So in conclusion of this video, notice that we've done 5 examples. All were involving proving or disproving, and 4 of those 5 examples involved proving a universal statement, and that required a general proof using generalizing from generic particular element or using direct proof, which is the same idea really. In all 4 of those, we built the outermost frame of the proof first, and then we were able to add at least 1, and in some cases 3 statements that we knew had to be inside that frame. Those statements that we knew had to be there narrowed the gap. So in the end, we had a much smaller gap to jump in building our proof. So that's the end of the video. Thank you.